Hi, this is Yi Hao, a fifth-year PhD student from UC San Diego, and this is a joint work with Professor Ping Li from Baidu Research. Okay, so here is outline. I'll start by definitions, then I'll talk about property estimation, then prior results, and then followed by new results, and then I'll give some examples, and finally I'll conclude the talk with ideas to take away. Okay, so the first idea is adaptive algorithm design. The second one is data amplification. So definitions. Let me first define a single distribution property. So we have an alphabet k, we have a distribution p over k, and let delta k denote the k-dimensional standard simplex. So a property is simply a mapping from delta k to the real values. For example, we have Shannon entropy, Zhenyi entropy, spore size, expectation, and variance, etc. Okay, so similarly, we can define a double distribution property. So now we have two distributions. Now we have the property, and this normally mirrors the similarity between distributions. Okay, for example, the L1 distance, L2 distance, KL divergence, and covariance. And more generally, we can consider a multi-distribution property. So let D be the dimension parameter, and namely, it's a number of distribution components, and let P be a d-dimensional tuple of distributions. So we have the property. This, of course, includes all the previous examples and more. And later in this talk, I will provide 6 examples arising in applications and covered by our results. So property estimation. So P is unknown. We are given property F and the samples from HPI. So our results actually apply to general sample sizes and general alphabet sizes. However, for the simplicity of the talk, we are going to assume that all the sample sizes are equal and all the alphabet sizes are equal. And we will write xn for the collection of samples. So we want to estimate fp from xn. So how do we do it? Of course, we use an estimator, right? So here is our estimate for f. And the simplest estimator is perhaps the empirical estimator. So let pi hat be the empirical distribution associated with the ith sample, and write p hat as the d-dimensional tuple of empirical distributions. So now the empirical estimator simply evaluates the property at p hat. It is also known as the MLE estimator in the literature. Here are some advantages of this approach. It's very simple, it's universal and applies to all properties. It's very intuitive and practically stable. It is the best known, most used distribution or property estimator. So how do we evaluate its performance? We use the standard sample complexity formulation, or the PEC formulation. So we allow an additive approximation error of epsilon, allow an error probability of delta. So again, for the simplicity of the talk, I'll set delta equal to 1/3. And then n f hat p epsilon is the sample size f hat needs to approximate f well. And n f hat epsilon is the sample complexity of f hat, which is an estimator. And finally, n epsilon is the sample size of the best estimator. It's the sample capacity of estimating f. So some prior results on property estimation. So the study of property estimation dates back several decades to the work of Good, Carton, Efron, and Sisted, and it has attracted significant attention over the years. Here are some references. And all these prior works mainly show that for many properties with d equal to 1 and d equal to 2, the optimal sample capacity is better than that of the empirical estimator by a logarithmic factors. For example, for entropy, when epsilon is not too small, then the sample capacity of the empirical estimator is k over epsilon up to constant factors. And the performance of the best estimator that achieves the sample capacity of estimating entropy is k by epsilon log k, which is better by a factor of log k. Okay. To summarize, so first we have logarithmic factor improvement. This is theoretically optimal, so we do not hope to improve this. Second, for d equal to 1, many properties have been studied, like entropy, spore size, and etc. And for d equal to 2, only a few properties have been studied. And more importantly and more generally, we want to ask a question, what would happen if d is greater than 2, right? So here are some new results. First, let me talk about the class of properties we are considering. So a D distribution property F is additive or additively separable if there exists a multivariate function sequence Fg satisfying the following equation. Basically, it says that we can decompose f into the sum of multivariate functions, okay? And for example, for entropy, d is equal to 1, and fgx is simply minus x log x. And an additive property f is Lipschitz if we have the following conditions. So basically, for every multivariate function fg, it must be Lipschitz in each of its inputs. So here we can replace one Lipschitz with any other kind of Lipschitz conditions. But for simplicity, we will keep using one here. And another example is L1 distance. Here d is equal to 2, and fgxy is simply the absolute value of x minus y. Okay. So then data amplification. This is the main idea in this paper. So for a broad class of multivariate multi-distribution properties, we want to emulate the distribution level performance of the empirical estimator, having access to larger samples, right? So basically, if an estimator has access to more samples, then we expect that its performance is going to be better, right? And this idea actually appears in some other prior works, so you can check it out. So this is the first theorem. So given an additive Lipschitz property F and samples from P, and imagine that there is another sampling parameter M, which is larger than N, and we can draw an independent sample Ym from P. And then we want to emulate the performance of the empirical estimator with a Ym as its input. So here is the theorem. Tau is a hyperparameter that we can choose. So for any a greater or equal to 2.5 and any distribution P, if we have the following condition, then the performance of our estimator, which is denoted by f hat, is roughly the same as the empirical estimator having access to more samples. And this is true with high probability. Okay, so to see some of its implications, here is the first corollary. So for an epsilon additive Lipschitz property f and sufficiently large k, the sample complexity of estimating f is at most k by epsilon cubed over square root log k. Okay, so here are a few remarks. First, d is often a small constant. Second, if f is regular, where regular means that for all ig, pig equal to 0 implies that fg, pg is 0. Okay, then the dependence on d is at most d to the power 3.5. And in addition, we show that we can express any multivariate real function as a sum of regular functions. Okay, so let me talk about some significance of this corollary. First, the sample complexity is sublinear in K. And in addition, in the second theorem of the paper, we show that the empirical estimator requires an omega k number of samples, even for some simple symmetric properties. Okay. And in addition, more importantly, for almost all dimensional properties with d greater or equal to 2, and sublinear sample complexity bounds like this are not known before our work. So this is why our work is significant. And our estimator is also very simple to implement and near linear time computable. And both attributes are highly desired for modern data science applications. And finally, the construction relies on a smoothing technique via Bessel functions of the first kind, which we refer to as the Bessel smoothing technique. This is of independent interest. Okay, so in other words, this provides a unified approach that applies to numerous important tasks, such as distribution mixture testing, distribution distance estimation, the intersection kernel estimation, the common unseen elements estimation, and finally, the high-dimensional independence testing tasks. Okay, so now let me explain those examples. The first example is distribution mixture testing. Okay, so if we have 3 distributions, then we want to check if P1 is close to any mixture of P2 and P3. So we can do this by estimating the following property. And this, of course, generalizes to more distributions. And basically, we want to find the minimal distance between P1 and any mixture of P2 up to PD. Okay. And second example is distribution distance estimation. We want to check the statistical similarity between data sources. So the literature has covered L1 distance. Here we also cover LQ distance with Q greater or equal to 1. And in addition, we cover the following distance, which is called the chi-square distance. It is also known in the literature as the triangular discrimination. Here is its formula. Okay, and the third example is intersection kernel. And basically for any distribution P, we denote by KIP, the intersection kernel. It's a sum of mean probabilities. And this measures the overall similarity of a collection of distributions. And it is very popular in computer vision and generic classification tasks. And as you can see, this property is maximized if all the PIs are identical, and it's minimized when all the PIs do not share any common element in their support sites. Okay, and the fourth task is common support coverage estimation. So imagine that we draw a sample of size m from every distribution PI, and then we have SMP. This is the common support coverage, and this is actually the expected number of distinct symbols appearing at least once in all samples. So when d is equal to 1, then this is equivalent to the well-known Fisher's unseen species problem. Okay, and it has many applications in ecology and biology studies, and it actually represents the number of comparisons that can be made among individuals from different populations. And the last example I'm going to talk about is a high-dimensional independence testing task. So we want to test the independence of random variables. So we are given sample access to the joint distribution and a collection of marginal distributions. And then we want to estimate the L1 distance between the joint and the product of the marginals. So this is frequently encountered in the data analysis. And practically, marginals are often over fbs of different sizes, which is accommodated by our formulation. So finally, I will conclude the talk by ideas to take away. The first one is adaptive algorithm design. So normally or traditionally, people design algorithms based on worst-case analysis. This is somewhat pessimistic because if you think about it, the underlying distributions may not be of the worst case. And modern data science calls for adaptive algorithms, for example, in data clustering, in neural network analysis. And so we want to design algorithms that have better performance on easier instances. For example, if the data is of low dimension or if the data is intrinsically simpler. Okay, so this is the first idea. So the second idea is data amplification. And so again, normally when someone is asked to design an optimal algorithm, he usually does this directly, and this might be hard. And instead, as we shown in this work, we can first find a simple algorithm that works, and it is the empirical estimator in our approach. And then we can emulate its performance by an algorithm that uses smaller sample sizes, right? So this two-step procedure can be an efficient procedure to design efficient algorithms, right? Okay, so for details, please refer to our papers for algorithms, proofs, and extra results. And that's all for my presentation. Thank you very much for listening.